Hello and welcome back. In this video, we'll be discussing level curves and work through an example. There'll be more example videos after this of producing level curves of a function of two variables, but we'll do at least one example in this video just to better explain what's going on here. So the idea here is it's difficult to graph in 3 dimensions, and we'd like a way of understanding the surfaces of functions of 2 variables without having to produce the entire graph. Or you might think of this as a way to visualize that graph in 3 dimensions without having to draw the whole thing, because again, it's difficult to do that. So this is going to be a really important tool for visualizing these functions of 2 variables. The idea is to pick a point on the graph of f. So you have this function, you want to better understand it, how it works, what it looks like. So pick a point on the graph of f at some height, at some z value, and then travel on the surface, right? The graph of f is some surface. Travel on that surface without moving up or down in the z direction. So remain at a constant height, and what you'll get is a curve that's traced out. So let me show you what I mean by that. So here we have a graph of a function of 2 variables. It looks like this. And what we'll do is we'll pick, so here I've picked a height. Here I'm at z equal to 2. And all of these points on this curve I have pictured are at z equal to 2. So this is the collection of all the points at z equal to 2 on this surface, and it looks like an ellipse. And so this is, if we drop this down into the xy plane, so notice I've just put the shadow of that curve in the xy plane, that what we have there is what the surface looks like at z equal 2. So we call this a contour curve, and then the shadow of that is the level curve on the xy plane. And so what we're going to do is we're going to select a bunch of different z values. There's a different one. There's z equals 1.5. It's a little bit bigger of an ellipse. I can do z equal 1, larger ellipse yet. And what I'm going to do is I'm going to graph each of these level curves in the xy plane and label them with the z values that generated them. So I'm going to graph a family of curves with labels for the heights of those things, and that'll inform me of what this surface looks like as we change the height. Okay, so we're going to do that for each one of these, and we're going to graph all of those curves in the xy plane. What we're going to get now is something that looks like this. So this is sort of our end result of this sort of analysis, is a collection, a family of curves, what this function looks like at various heights. So again, I can change my z value. I can see here if I start at z equal 0.5, I get a big old ellipse like this. As I move up in the z values, my ellipses are getting smaller. And so what that's telling me is my function is rising in this sort of hill type shape, this elliptical paraboloid type shape like this. And so as we get higher and higher, these ellipses get smaller and smaller before eventually turning into a point and then disappearing where there are no points on the surface at that height. So that's the idea, is from this family of curves. Now here, these aren't labeled. If I scroll over, it'll label it. When we make these families of curves, we're going to label them because that'll tell us, like, if we want to go higher on the surface, what do our curves look like? If we want to go lower, how does that change it, right? That's going to change this from being a bowl shape to like a dome shape, like it actually is, depending on the labels, right? All right, so that's the idea. We're going to do that for our functions of 2 variables. Now, there's a good chance you've seen these things before. What we're actually doing is we're taking a 3-dimensional object and we're kind of projecting it into a 2-dimensional plane, but keeping track of 3-dimensional information, those heights, those curves. Where you've seen this before is looking at a topographical map. It's likely you've seen a map that looks something like this before. Here we are, I don't know, Devil's Thumb, I'm not sure where exactly we are, out west. American West somewhere. We have a canyon over here. And you've seen these things before. I guess the big thing I want to point out with this is if you have right? So each of these lines are representing a certain height, and there's a specific distance between heights that's kept track of. So the idea is if my curves are spaced out here, so spaced out curves, compared to, oh, say over here around Devil's Thumb, where we have some kind of geological formation. Notice here, it's actually not even rendering that well. Maybe look over here, the lines are closer together. So over here, the lines are spaced out. Over here, lines are closer together. And so what these lines closer together, again, this is going to mean a steeper ascent. So over here is steeper than over here. This is less steep or more gradual of a change in height. Right, so over here, really, really, really steep terrain. Over here, not so steep, more gradual of an incline. Whether we go up or down, right, as we go through these curves, that depends on the labels for each one of these curves. And if I had a better render of this, if it were a little more detailed, we'd see some numbers here. And we could work out, if I travel in this direction, are we going up or down? If I travel in this direction, are we going up or down? And then the spacing of the curves tells me how steep we're traveling, either up or down. So this is the idea. So think topographical map. That's really what we're doing here. And then the whole idea is to take a three-dimensional object and sort of consider a bunch of two-dimensional slices of it. Similar to what we did with quadric surfaces and the traces, right? It's very similar to that idea. We understand a three-dimensional object through a collection of two-dimensional objects. So in this video, we're going to do one example. Like I said, we'll have more examples of this in later videos. I don't want to make this one too long. All right, so here's my XY plane. My surface is living either above or below this thing, and I'm going to keep track of these level curves. So I'm going to set z equal to various quantities. How about I start with z equal to 0? So in order to find these curves, I'm going to need to do some algebra. So remember, f of xy, that's my output. This is my z variable. And so I'm going to set that equal to 0 for this first one. I'll get 0 equal y minus x squared minus 1. Let's go ahead and rearrange that a little bit, right? I want to view this as a curve. And so I want to make this look like the equation of a curve I'm familiar with. Here I have a y to the power of 1 and an x squared together with a constant. That reminds me of a parabola. So I'm going to solve for y here and get y equal, I'll get x squared plus 1 plus x squared. And I'll go ahead and draw that curve in the xy plane and label it with z equal to 0. So let's do 1, 2, 3. Just to try and get a little bit more exact. So at z equals 0, we have 1 plus x squared. So that'll be a parabola like this. So there's I get a parabola. So think about a plane parallel to the xy plane at z equals 0. Okay, so the xy plane itself. So if I intersect the surface with the xy plane, the resulting curve is this parabola. And that's at the height of z equals 0. So I'm going to mark that down. Let's do another one. Let's do, say, z equal to 1. What do we get here? I'll start with 1 equal y minus x squared minus 1. Add that x squared over, add the 1. I'm going to get x squared plus 2. Here I get y equal 2 plus x squared. And so that's 2 plus x squared. That's going to shift my parabola up another 1. And I'll label this with z equal to 1, not 2. Z equal to 1 right here. So that's a height of 1. Now you can imagine what's going to happen if I do z equal to 2. I'll get 3 plus x squared. Right? I don't even have to work out that algebra if we can notice the pattern of what's happening. So that's at z equal to 2. We'll have another parabola here at z equal to 3. And then if I go down, right, so if I do, say, z equal to negative 1, the 1s are going to cancel out. I'll just have y equals x squared. So I'll get this parabola at z equal to negative 1. And again, we'll get another parabola as I go downward. So this is at negative 2. Right? This will be negative 3. And I'm just kind of sketching it. It doesn't need to be exact, but they should be parabolas, and we should have this idea that they're being shifted up or down. So these are the level curves for the graph of this function. Can you imagine now what the function looks like based on these level curves? So they're looking like parabolas, and as I move up, if I want to ascend this surface, as I move up in the z values, I get parabolas that move upward in the y direction. So try and imagine what this is going to look like. And now I'm going to reveal now what the actual surface looks like. And I'll use a graphing utility for that. I've used GeoGebra and put the surface in. And that's what we get. And so here's some of those contour curves now on the surface, so not projecting the XY line, but just on the surface. That's what we should be trying to imagine from this collection of level curves, right? Imagine these stacked up on top of each other at different heights, and we get this object. So pretty cool. This allows us to imagine graphs of functions of two variables that aren't necessarily easily recognizable quadric surfaces, right? Quadric surfaces that maybe we didn't study back in 13.6. We'll be able to recognize or inform ourselves of what the surface looks like based on these level curves. That's the idea. So like I said, more examples to come. Here's one just to get a taste of the method. You can now start practicing if you'd like, and watch the videos if you need some help with these things. All right. Thanks for listening.